Shown in the figure below is the front view of a sliding bar system. The bar has a resistance R, length L, mass M, and is free to slide vertically along the rails. The system is immersed in a magnetic field directed out of the screen toward you. The bar is released from rest and begins to fall downwards due to gravity. We are then asked a series of questions, the net result of which is a single answer, and that is the velocity as a function of time of the falling bar. The attractive aspect of this problem, particularly in becoming a problem that goes on an exam, is that it exercises many of the laws of physics that we've learned in this class. Let's follow the derivation from the beginning. This problem is a problem that begins with a study of Faraday's law. And Faraday's law is based upon a rate of change of magnetic flux. Magnetic flux, as always, is a field times an area. The field is the magnetic field, and the area is the area formed by the loop. Looking at the figure, we can see that this area has a length L and a width Y, finishing our expression for magnetic flux. Because this is a single loop, we can find that the voltage in this loop is related to the time derivative of the magnetic flux. And since B and L are a constant, this is related to the time derivative of the position. And as we learned in Chapter 2 of the class, time derivative of position is known as velocity. Ohm's law tells us that there will be a current induced in any loop that experiences a voltage, and so using the voltage from the previous step, we find that the current induced in the loop is BL over R times the velocity at which the bar is falling. Any length of current, as an example our bar, that exists in a magnetic field will experience a magnetic force equal to ILB, and using the expression for I from the previous step, we'll find negative B squared L squared over R times the velocity as the value of the magnetic force. The magnetic force is not the only force in this problem. There is also gravity. In order to find the total force, we're going to begin with a free body diagram. That dot will represent the bar itself, and the gravity force on this one will be mg. The magnetic force will be directed upwards and is of a strength, absolute value, B squared L squared over R times the velocity. As with any free body diagram, we're going to select the coordinate system to be aligned with the acceleration, and this object accelerates in the direction down. Therefore, the plus direction will be with the mg, and the minus direction will be with the B squared L squared over R times the velocity. So far in this problem, we have exercised the definition of flux, Faraday's law, Ohm's law, the formula for magnetic force, and also the sum of all forces is equal to ma. We currently recognize that this is in fact a differential equation, since the definition of acceleration is the time derivative of velocity. This equation can be simplified by dividing away the m to yield a time derivative of velocity, which is g, what you would have with gravity alone, minus an amount due to the magnetic force, which is b squared L squared over R times m, and that is multiplied by v because the magnetic force is going to be velocity dependent. The faster you go, the stronger is the magnetic force. At this point in the problem, we have actually finished the application of all of the physical principles necessary to get the answer. However, since we have been asked to find explicitly the velocity as a function of time, when an expression such as the one shown here tells us the derivative velocity as a function of velocity, this becomes a calculus problem that we can use to solve for the velocity itself. This solution is actually going to take quite some number of steps, meaning that the problem at hand has a large amount of mathematics in comparison to the physics. Nonetheless, this is mathematics that, number one, is within the scope of the class, and number two, really teaches us an understanding of calculus. The differential equation that I'm circling in blue is a first-order differential equation because it has single derivative rather than second derivative. We can move all velocity-dependent terms to the left and move all time-dependent terms to the right. The method by which we achieve our solution is we integrate both sides of the equal sign, and we need to put explicit boundaries on the integral in order to perform it. We're going to integrate the time from 0 to some later time t, and because this object is released from rest, at time equals 0 the velocity will be 0, and at some later time the velocity, we'll just call it v. The right-hand side has a very simple solution because the integral of dt is t, and evaluated from 0 to t gives us an answer t for the entire right side. The left side will take a little bit more work. We will use a u substitution in which u is equal to g minus b squared L squared over mrv, and therefore du is equal to a constant times dv. This means that we can substitute for both the numerator and the denominator in our integral to make the numerator in terms of du and the denominator in terms of u. We will integrate over this, but currently we're not going to put limits on this integral because the limits on the integral would need to be expressed as u limits, and that's going to be just a pain in the butt. Removing the constant from the integral will leave simply the integral of du over u, which we recognize as natural log u. Now that the integration is complete, we'll substitute away u to be in terms of our original variable v, or velocity. Because velocity is the variable in which we know the limits will go from 0 in the beginning to v at the end. Plugging in these two values and recognizing that the difference in logs is the log of the ratio, we have our result for the left-hand side of the integral, and we remember that the right-hand side was somewhat simpler and integrated merely to t. On your own, you should solve this equation for v, and if you've done it correctly, you'll come up with the result that the velocity is equal to mrg over b squared L squared times a saturating exponential function. This function is very familiar from our studies of transient circuits, and we can plot this result for velocity as a function of time as a rising saturating exponential, where the value at saturation is equal to mrg over b squared L squared. As a final note, it's interesting to realize that this eventual or terminal velocity can be rearranged to yield b squared L squared over r times the terminal velocity is mg, which in fact is exactly the condition we would expect for a terminal velocity, and that is the terminal velocity is achieved when the magnetic force is equal to the gravity force.